Hi guys, welcome to this quick recording concerning, I think the last problem of the review. The last problem of the review, I promised to make a recording for it because we ran out of time when we did it in class yesterday. And I didn't have a chance to go around it yesterday, so hopefully you guys would have figured it out by now, if not, because nobody reached out to me. If not, hopefully this recording will be helpful. So anyway, the problem before this one was a little bit long, and we had to really go through it systematically. So that's why we couldn't finish this one and this last one. So let me share with you the screen so that you guys see how this look like. Okay. First of all, a quick reminder. Hopefully, you guys can see the OneNote. Okay, this is obviously is recorded. Let me minimize my email just in case if it's showing. Anyway, so basically, what we have, the previous problem is that we had an isothermal process, and then also followed by an isobaric process, and finally an isochoric process. So in the isothermal, basically what we said is the change in the energy is zero because the temperature doesn't change. So that means that W is equal to minus Q, and W for an isothermal process, we did the calculation. That was one of the first things we did, is ln of V final. I'm sorry, initial, because there is a minus sign in front, divided by ln of divided by VF. And so that's basically the work. The heat associated with it is just you flip the fraction in there because the ln has this property, which is ln of x is equal to negative ln of 1 over x. Anyway, so we have that for the isothermal process. For this process in here, the work is going to be equal to negative P times delta V, where this is the V final, and this is the V initial. Obviously, for the isothermal, this would be the V initial, and this would be the V final. So you have to be careful in here. So the notation, or call them 1, 2, 2 and 3 would be the same. So it's going to be 2, and this would be 3. So this would be V3 minus V2 in this notations. Okay, time is the pressure. And I think the pressure was given to be 1 atmospheric pressure. And in point I, the initial point, the pressure was 5 atmospheric pressure. Okay. This point in here was 1 atmospheric pressure. The volumes went from 10 liters to 50 liters. So you have to be careful with that, making sure that the conversion into cubic meter is that 1,000 liters is 1 cubic meter. Okay. So other than that, everything, and ATM, I think in the class, because we were running out of time, 1 atmospheric pressure, I took it to be 100,000 Pascal. That's really 1.013 times 10 to the power 5 Pascal. Okay, you have to be aware of these conversions, and then everything follows. You have the work in here, but you also need the heat. So the heat in this case is going to be equal to NCP delta T, where T is this temperature minus that temperature. And the work in this section here, the isochoric process is 0, and the heat is equal to NCV delta T. I think I made a mistake, and then we caught it before the class was over in here for that value for the heat. So we have that. So, and here the energy change is just Q. There is no W. And here it's the sum of these two quantities for the second process, okay, for the isobaric process. One thing that I took advantage in here in this problem, and hopefully you guys have already picked up on it, is all of these temperature measurements, whenever we're doing TF minus TI, because we're multiplying this by the pressure. So what we do in this case, at some point, we're going to get CP or CV involved, and both of them involve R. Either, was it the 3/2 or 5? I think it was a diatomic gas. I'm looking at the problem in here. Monoatomic. So CV was 3/2 of an R, and CP is 5/2 of an R. So both of them involve R anyway, okay? So for the, at some point, we're gonna multiply R times TF minus TI, and times, of course, the number of moles, because these values are specific, heats, molar specific heats, meaning at the end of the day, we have to multiply by the number of moles. But for this problem, it made it easy. The number of moles was 1, so n is equal to 1. So it's kind of easy in this case. So we really don't have to. But the point in here, I took advantage of this fact that this product, NR times the temperature, is actually the pressure times volume. Since we don't have the temperatures, we could calculate them, given the fact that we know the volumes and the pressures, but there is no need, okay? It's just P times V, P times V everywhere, okay? Because a combination nRT is what we need, and that is PV. So that is actually to take advantage of the problem. Otherwise, you will be calculating the temperatures, and then at the end, multiplying, dividing, and then at the end, you didn't do nothing because you're back to P times V, okay? So that's one thing. So hopefully you guys picked up on this technique, and it's always true in the PV diagram. If you're not asked about the temperature, and even if you don't know the number of moles, and you're given the P and the B, so that's all you need for calculations of energies and even the entropy at some point, okay? So that's problem 37. Problem 38. Problem 38, which is really why I have this recording in here. It's on page 585 from your notes. Basically, it says a system consisting of an n moles of an ideal gas with molar specific heat at constant pressure Cp. So this is what's given. We have n moles and we have Cp, okay? Constant pressure Cp undergoes two reversible processes. It starts with pressure Pi and volume Vi. So it helps actually to graph things. It helps to actually visualize things. So it's a good idea to go into a PV diagram and draw this point, this starting point. So this is P, this is V. So this is the point that we start with. It has specific volume, Vi, and it has a specific pressure, Pi, okay? So that's given. And expands isothermally and then contracts adiabatically. So it's going to expand and then it's going to contract on an adiabatic, okay, process. Remember, one of the problems we did also, I think problem 42, we did it actually in class, is that the adiabatic is always steeper than the isothermal. So in this case, they say that, so they didn't tell us where it expanded isothermally, but this is isothermal, T is constant. And this one, Q is 0, adiabatic, okay? Contracts adiabatically to reach a final state with pressure Pi. So at the end, we're back to the same pressure, Pi. And volume 3 times Vi. So this volume is 3 Vi, okay? That's basically how the picture looked like. So you expand isothermally to a volume that most likely it has to be bigger than 3 Vi, and then you compress back to the same pressure, Pi, at a higher volume, 3 times the initial volume, okay? So that's the key thing in here, okay? And then contracts adiabatically to reach a final state with a pressure Pi and volume 3 times Vi. Find its change in entropy in the isothermal process. Okay, obviously there is no change in entropy in this state in here, okay? Because there is no Q. So delta S in the adiabatic process is 0. That's why it's called actually isentropic process, the adiabatic process. So what do we know? We know that this pressure, let's take an intermediary point in here. Let's call it, so this is VF, so this is the final point. So we're gonna call this point middle, okay? So there is a volume in the middle and there is a pressure in the middle, okay? Since this is part of an isothermal process, the temperature doesn't change. That means the Pi, Vi, the initial point, is governed by equal to nRT, and N doesn't change, R doesn't change, and T doesn't change. And that's the main thing, is equal to the pressure at the middle point times the volume at the middle point. We know that for a fact, okay? We also know that this point in here the middle point, and the final point are governed by the fact that the pressure in the middle times the volume in the middle to the power gamma is equal to the pressure at the end, which is Pi, it's the same Pi, and the volume, which is 3 times Vi to the power gamma. So we know this fact too, okay? Obviously, we introduced the parameter PM, which is really not part of the solution. We really need to get rid of it. We need to find that volume VM, by the way. That is the whole thing, because there is no expansion, there is no entropy in here. So all the entropy in here, and the entropy is going to be at the end, basically, if we do the math correctly, it's going to be the integral of dq over t from the initial state, which is I, to the final state, which is middle, from I to M. And that's the change in entropy, end of the story, for the whole process, actually, not just for the isothermal process. And since we don't know what that volume is, because at the end, the integral is going to be from Vi to Vm. So we really need to find this middle volume. Okay, that's the thing. So armed with this relationship, I'm going to get rid of PM first. You can clearly see from this equation that PM is equal to the initial pressure, Pi, Vi, over this middle volume that we don't know, but we need. Okay? So we come back to this expression now instead of the value of PM. So this is the adiabatic process given by the pressure at this point, which is the middle point, times the volume to the power gamma in the middle point, equals to the pressure at the end, which is part of the adiabatic process, times the volume at the end, which is 3 times Vi, to the power gamma. So this is the adiabatic process. Now, having said that, let's sub the value of PM, which is Pi, Vi, divided by Vm, times Vm to the power gamma. I'm looking at this side of the equation, okay? Let me see if I change the color. I'm looking at this side of the equation here, okay? Needs to be equal to the other side of the equation, which is Pi, that's the final pressure, times the final volume to the power gamma. And the final volume is this one. So now, basically, we have what we need for that volume. We need the volume Vm. Obviously, we need to do some manipulations. First of all, Pi cancels, and that's good, because it was never given, numerically at least, so we can't really do calculations with it. Okay. And now I have to clear this thing in here. I have Vm to the power gamma, I have Vm in here. So it's going to be Vm to the power gamma minus 1 is equal, first of all, the 3 to the power gamma by itself. So we need to get it out. So the 3 to the power gamma. And then I have Vi to the power gamma divided by this Vi. So it's going to be Vi to the power gamma minus 1. As a matter of fact, I need the ratio when I do the calculations for this quantity. I need the ratio of Vi over Vm over Vi. So the ratio of the two volumes, V middle over Vi to the power gamma minus 1 is equal to 3 to the power gamma. All I need is really their ratio, not to the power gamma or anything like that. So I'm going to take to the root of 1 over gamma minus 1. So basically, raise this one to the power 1 over gamma minus 1, and this one to the power 1 over gamma minus 1. And this will give me just the ratio of the two volumes. So this is going to be 3 to the power gamma over gamma minus 1. Now, what this thing says is, during this expansion, what is the problem? During this expansion, we have found this volume in terms of the initial volume, okay? And that ratio is just 3 to the power gamma over gamma minus 1. Now, T is constant during the isothermal process. So it comes out of the integral. So the change in entropy really is just Q evaluated in this process divided by T, because T is constant in an isothermal process. Remember, we're focused only on the isothermal process. And if you care to include to the adiabatic process, all you're adding is 0. So there is no change in the adiabatic process. Okay? So now having said that, During an isothermal process, there is no change in the internal energy because the temperature doesn't change, so there is no change. That means that Q is equal to minus W, minus the work. And the work in this case, if you guys remember, it's just nRT, the log of the initial volume over the final volume. So this is N. We did that in lecture. And if you have difficulty with it, please let me know. Just integrating that work, minus PDV integrated from the initial volume to the final volume with a negative sign in front of it. That's why the ratio in here is flipped, VI over VF. And except VF in here is that middle point, okay? Remember, we're focused only on the isothermal process. In the isothermal process, this is your VI, this is your VF, which is, I call it VM, V middle in here, okay? Having said that, then the Q is just this ratio flipped. So the Q, because I have the negative sign in there, so it's nRT ln of V middle over VI. We have everything. We have that ratio. It's 3 to this power, okay? But don't forget, we need Q over T to get to the entropy. The entropy is Q over T, not Q. So the change in entropy, delta R, delta S, I'm sorry, is equal to nRT ln of Vm over Vi over T, get rid of the T. That's good, we don't know it and we don't care for it. So at the end, we have the entropy as equal to nR times the ln of this ratio. And this ratio, we just computed it, 3 to the power gamma over gamma minus 1. Okay? The properties of the log in here is in full-fledged. So delta S is equal to nR gamma over gamma minus 1 times ln of 3. And that's the answer. I mean, they didn't give us the number of moles, so you can compute this one for 1 mole and say this is per mole. This is how much entropy is changing. So you have, and you don't even have gamma. They didn't even tell you what type of gas it is this. So if it is a monoatomic gas, gamma is equal to 1.67. And you can do the math in here. And if I take n equals to 1, then obviously the change in entropy is going to be equal to 8.314 times 1.67 divided by 0.67 times ln of 3. So it's a number, okay? It's going to be in joules per Kelvin, okay? So hopefully you guys can finish this calculation. And I know it has a part B, but part B is dealing with another problem from this chapter, but we're not doing that problem anyway. So hopefully this is helpful. Please let me know if you have any other questions or something else. Thank you.